All right, today we're going to pull back the curtain on this secret language that basically powers our entire digital world. And no, it's not Python or C++, it's something way more fundamental. Propositional logic. You could say it's how we teach a computer how to think.
I mean, really think about that for a second. How do you take a messy, nuanced human idea and translate it so a machine, a literal box of rocks we taught to think with lightning, understands it with perfect, absolute clarity? Well, that's the big puzzle we're going to solve today.
Take a super simple sentence, like, I'll have a salad or a soup. Now, you and I, we get it, right? The context clues tell us you probably have to pick one. But a computer? It just freezes. It sees ambiguity. It needs an ironclad black and white rule. It needs to know, is the final outcome true or is it false? There's no room for maybe. So to solve that ambiguity, we need a system. And that entire system is built on one simple but incredibly powerful building block, the proposition.
So what is a proposition? It's really just a statement that declares something. But here's the golden rule, the one thing that makes it all work. It has to be either true or false. That's it. No kinda, no sort of, no in-between. It is pure binary. For example, the sky is blue is a proposition. We can look outside and verify if it's true or false. 2 + 3 = 5. That's a proposition too. And hey, it happens to be true. But what about a question like, what time is it? Or a command, please close the door. See? You can't answer true or false to those. So they are not propositions. Simple as that. Okay, so we have our basic words, these propositions, but to build anything interesting, you need more than just words, right? You need grammar. And in logic, this grammar is made up of things we call connectives. Our first and probably simplest connector is the conjunction, which everybody just calls and. Its symbol kind of looks like a little mountain peak, and it does exactly what you think it does. For any and statement to be true, every single part of it has to be true. It's all or nothing. If I say, I will eat and drink, that statement as a whole is only true if I actually eat and I actually drink. If I only do one of them or neither, the whole statement is false. Now, things get a little spicier with the word or. You see, in English, or is a bit fuzzy, but logic hates fuzzy. So it splits or into two totally separate ideas. There's the standard inclusive or, and then there's its stricter cousin, the exclusive or. The inclusive or just means at least one of these things has to be true. So with this rule, if you've taken calculus, you're in. If you've taken computer science, you're in. And what if you're an overachiever and you've taken both? You're still in, because at least one of the conditions was met. But the exclusive or, that one means exactly one of these things must be true. Back to our dinner special. You get the salad or you get the soup. You don't get both. If you try to take both or you take neither, the condition is false. And there you have it. That solves the ambiguity problem we talked about right at the start. Okay, let's keep building. We're ready for one of the most powerful and common structures in all of logic, the conditional statement, better known as if-then. This creates a condition. If P, then Q. Learning discrete math, that's our P, leads to the outcome of finding a good job, our Q. This if-then structure is literally the backbone of almost all decision-making in computer programs. But here is where people get tripped up. You can rearrange an if-then statement in a few ways. The converse flips it, the inverse negates both parts, and the contrapositive does both. It flips and it negates. Now listen closely, this is important. Just because our original statement, if it rains, the ground is wet, is true, its converse, if the ground is wet, it rains, is not always true. Why? Well, maybe a sprinkler was on. And this brings us to a really beautiful, crucial insight. Of all those different variations, the original statement and its contrapositive are logically identical. They are just two different ways of saying the exact same thing. If it rains, the ground is wet has the exact same logical meaning as if the ground isn't wet, then it didn't rain. This isn't just a party trick. It's a fundamental tool for making solid arguments and writing bug-free code. All right, enough theory. Let's see how this very abstract language actually gets used to build the real world around us. So, remember our original problem? Translating that messy human language. Well, now that we have the tools, our propositions and our connectives, we can actually do it. We can strip away all the ambiguity. And this slide just shows you perfectly how it's done. Look at the first sentence. If the system fails, that's our condition, our P, The result is either the power is off or the software crashed, which we can write precisely as QVR. We've just translated a complex sentence into a perfect logical expression. Same with the second one. The computer starting depends on being plugged in and the switch being on. That's a classic conditional. Now, you might be thinking, okay, this is for computer scientists and mathematicians. But the truth is, you already use this exact same logic probably every single day.
Every single time you use a search engine, you're using these logical connectives. When you search for logic and computers, you're telling the system you demand pages that contain both of those terms. Using OR broadens your search, and NOT lets you exclude things you don't want to see. This is propositional logic in action, right in your search bar.
And you know, at the deepest, most fundamental level of a computer, this is what it all comes down to. A single bit. A tiny switch that is either on or off. A 1 represents true, and a 0 represents false. Every single complex operation your computer performs, from rendering a video game to sending an email, is built from billions of these incredibly simple true or false decisions.
So when you boil it all down, propositional logic isn't just some abstract topic in a math class. It's the rigid, reliable, and totally invisible language that powers our digital world, from the code that runs your car to the search bar on your phone.
And that leaves us with a final thought. Now that you can see the structure, the ands, the ors, the ifs, and thens, what other parts of your world, maybe things you've never thought about before, from legal documents to the rules of a board game, are secretly being run by these very same rules of logic?